In 6.2, we're going to be talking about this famous constant called E, and E is approximately 2.7, 2.71828, something like that, is what it is. But basically, it was found through nature. So I just found this little part on the internet that I pasted up here at the top that kind of gives you the wonder and mystery of what E is. And so it's going to replace, in the last section we talked about bases like 2 to the x or 1/2 to the x and how that's exponential growth and decay. Well, we can take that base and replace it with E. Okay, so the way that this is found in nature is in something called the logarithmic spirals, and it all is based around this number that we call E. This says that it appears in nature, found in places as shells, horns, tusks, sunflowers, and even spiral galaxies. So if that's something you might be interested in, please take the time and investigate and just Google it and see what you can find out. I think it's pretty neat. They don't know where it originated from other than through bankers and investors started coming up with the same number. You'll see on the next screen what they were doing to find it, but it ended up coming up to the same 2.7 and it got closer and closer and closer when they were working with compounding interest. But then through more investigation mathematically, they found out that it actually has a bigger purpose in the world. So it's pretty interesting, and I encourage you to take the time if that's something you want to look up. Okay, so our biggest focus on this study of this base of E, here is the approximation. Now it's an irrational number, so it's going to go on forever. This is just what we can narrow it down to. And so again, it came from this idea of taking an amount of money and adding to it at some number of times a year like this. It looks very similar to that formula we learned on compounding interest. And what happened is as you plug any value in for X here, so whatever kind of values you want to plug in, you're going to get something close to 2.7. And so that's how it was discovered. Kind of like how pi was discovered by the Egyptians, and what they did was they took a bunch of circles and they determined the circumference and divided it by the diameter, and they got closer and closer to the same number. And so that's how pi was discovered in nature. So it's pretty interesting. But anyway, so continuing on with this idea of this base of E, that's called the natural base. And so we also have a growth and a decay depending on this R right here. So if that number is positive, then it's going to be a growth, and that kind of makes sense. If that number up there is negative, then it's going to be a decay. And this is what the graph looks like, very similar to the other growth and decay that we learned in the last section. And like I said, the biggest use for this is to use something called continuously compounded interest. So last section we talked about compounding monthly, quarterly, semi-annually, and now we're talking about compounding continuously. That means every single second of every single day it's constantly being compounded. And so let's just work an example here that we'll make up. We'll take, I think earlier we had used $2,000, so we're going to take a principal amount of $2,000. We're going to give a rate of, let's say, 2.25%, and let's say we want this for 5 years. And so we need the same given information other than the number of times a year. That's going to be represented by this E. Okay, so the way we work the formula is we'll have the amount that we left over with is what we want. The principal amount is $2,000. Then we're going to have E to the R. Remember, we want to put that in as a decimal, so it'll be 0.0225 times 5. And I actually put this parenthesis here, and I don't need it. Take that out. Okay, so this is like times there. All right, so when you're solving this in the calculator, you first got to find this amount. So we have 2,000, and then I'm just going to take my calculator real quick and type in, and I'll show you how to do this with ours in class if you don't know how. But that gave me like 1.11907 da da da, and I'm just going to take that amount and multiply it by 2,000, and I have $2,238.14, and that's what they continuously compounded, which is also called simple interest. Actually, guys, for now, for this set of questions 5 through 8, I just want you to list the growth and decay. We won't worry about graphing these. So in this case, we're looking at the fact that there's a negative there where the R would be, and so this one is going to be a decay. This one here is going to be a growth. It doesn't matter, and this is a little different than the last section, it doesn't matter what the A numbers are. All that matters is that R, meaning what's in front of the X. If it's positive, it's a growth, and if it's negative, it's a decay. Okay, so here in number 12, we have a certain city who has a current population, and they're saying they're declining, which tells me it's going to be a decrease, and it tells me by how much. And it's given us that same formula here. They just changed the variables just a little bit. It says P sub C is the current population. So that means this is P sub T is the population after T years, is what we're looking for. So for P sub C, we're going to put in that 48,500. Then it says E is the growth rate at the R. Now R, it says, is declining at 2.5. So again, we do want to use the decimal version of that, which would be 0.025, but the fact that it's declining tells me it's going to be negative because it's got to be a decrease, and then it will be after T years. So that's kind of the setup for the problem. So what does it want? It says predict the population of Evans City after 25 years. So we're basically going to take this same problem and we're going to work it out when T is 25 years. So I'm just going to take the calculator and plug that in, and you do the same, see if you get the same amount as me. I got about 25,960. Let's double check that to make sure that you know how to do it. You're basically going to solve this part first and then multiply it by 48,500. Okay, in the next one, we have parents who will need, now this is a little bit of a change. There's our time is 10 years, but they're going to need 25,000. That means they're not starting with 25,000. That's what they want to end up with. And that's for college tuition. They can invest in an account with an interest of 9.8. That's a pretty good interest that compounds continuously. This tells me, when I see this word continuously, that tells me I'm going to use that PE, I call it the PERT formula, sometimes like the shampoo, the PERT formula. And we want to know how much your parents should invest in order to have the full amount after 10 years. So the setup's going to be a little bit different in that we want to end up with $25,000. We don't know the principal. That's what we're trying to figure out. How much do we need to start with in order to get that to happen? With a compounded continuously rate of 0.098. Now this is going to increase, so we're going to leave it as a positive, and then that's after 10 years. Okay, so we got to kind of be smart about this and use some algebra skills. Since we don't know P, we can figure out what this is. So we're actually going to take the calculator and type that in, and that gives me something like 2.66445. And then all I would need to do is divide by that number to both sides. Sorry, I gotta make this really small there to get what P would be. So P, once you work that out, should be about $9,382 So they need to start with about $9,300 in order for this to happen for their college tuition in 10 years.